Hello, everyone. Welcome to the distinguished colloquium series of the Turkish Math Society. Today, we are very pleased to have Mihalis Dafermos from Princeton University and University of Cambridge. Mihalis got his PhD in 2001 from Princeton University. He is after a CLE Moore instructorship at MIT, he joined University of Cambridge and then became a professor at Princeton University. He is the recipient of numerous awards, including the Adams Prize, the Whitehead Prize, and he is a fellow of the American Mathematical Society. So it's a great pleasure to introduce him, who will talk about the mathematics of black holes and general relativity.
Okay, thank you very much, Izzat, and thank you to the organization for this invitation. It's a great honor and a pleasure to speak. I hope you can all hear me okay. All right, so indeed my talk is about the mathematics of black holes in general relativity, and I'm not going to assume any previous knowledge of general relativity. So the first order of business will be to give you a crash course on general relativity and black holes. This will be maybe the shortest crash course you've ever had in this subject, but hopefully will be sufficient in order to be able to follow the things I want to talk about. Okay, so let's just go right into it, and then I'll tell you more about what this talk hopes to be about. So crash course in general relativity. This is Einstein. This is his famous November 1915 paper, Die Feldgleichungen der Gravitation, where he introduced the Einstein equations. So these are the governing equations of general relativity. So let's talk a little bit about what these equations are. So equations have a left-hand side. So let's see if I can even write here. This is left-hand side and a right-hand side, typically. And so it's maybe easiest to talk first about the right-hand side. So the right-hand side of this equation is something that has to do with the matter in the universe. It's technically speaking, it's the energy, momentum, content of the universe. Now, what is the left-hand side? So the left-hand side is maybe more interesting or more new. So the left-hand side is the curvature. More specifically, for those of you who know the so-called Ricci curvature, for those of you who know, let's say, Riemannian geometry, but in the Ricci curvature of a Lorentzian metric on space-time. Okay, so it's the Ricci curvature of some Lorentzian four-manifold, okay, which we call space-time. So if you want, this equation says that the energy momentum content of the universe, the matter, somehow constrains the curvature of space-time. So these are the Einstein equations. So let me just say a few words immediately. So often this is depicted in these sort of famous pictures. So we like apples in the study of gravity. So you can think of the matter as this apple, and the presence of the matter is curving, it's bending space-time. Okay. All right, so these type of pictures are very famous. So the first thing that I want to tell you, and this is something actually quite surprising, is that the Einstein equations are non-trivial even in vacuum. So even in the absence of any sort of matter, so there goes the apple, the Einstein equations are still non-trivial. So the equation Ricci curvature equals 0 is still non-trivial. And to paraphrase my academic grandfather, Johnny Wheeler, basically, this is related to the nonlinearity of the equation. So space itself is somehow telling space how to curve. Okay. So this will be very, very nice for the purpose of this talk, because for the rest of this talk, general relativity will mean vacuum. So we will never consider matter in the universe. Believe me, the universe would be a much, much better place if there were no matter anymore. Okay, so for the purpose of this talk, general relativity is really the study of this equation. So of course, this is a geometric relation, okay? But at the same time, it's a partial differential equation, and it's a partial differential equation of wave type. So essentially, what this means is that non-trivial curvature propagates in vacuum as a wave. So here is some non-trivial curvature, and here it is propagating away as a wave. And maybe I'll end this part of the crash course reminding you that, okay, this is all very physical, and in fact, these waves have been directly observed on Earth in 2015 by LIGO. Okay, all right. So this is the first thing I want to tell you about general relativity, at least in vacuum. It's really just the study of this geometric relation, aka this sort of system of partial differential equations for this metric. But let's be very concrete. Let's give an example of a solution of this equation. So let me tell you the first non-trivial solution of the Einstein vacuum equation to be written down. And remarkably, it was written down very, very fast, because if you remember the chronology, the equation that we just saw was first written down in November 1915. So already in January 1916 was published in a journal the first non-trivial solution. So this is the celebrated Schwarzschild solution discovered by Karl Schwarzschild. And it takes this form that I've just written down. So this is an example, by the way, of a Lorentzian 4 metric. Okay, so it's a Lorentzian 4 metric. And if you're paying attention, maybe I'll just say 2 words about this so that those who are not familiar with Lorentzian metrics can start to get their bearings. Well, this is actually a 1-parameter family of solutions. So this M is simply a parameter. Okay. So this M is a parameter, and we're always going to take it greater than equal to 0. Okay. And actually, if you put M equals 0 into this expression, then this is just the celebrated Minkowski metric, okay, in polar coordinates. Okay, so if you put M equals 0, and the Minkowski metric is just sort of the geometrization of special relativity. So in particular, why is this a Lorentzian metric? What makes it Lorentzian? Let's first look at the case where M equals 0. Well, it's this minus sign here. Okay, so this minus sign here, if this were plus, this would just be the Euclidean metric in 4-dimensional space. Okay, so it's that minus sign that makes all the difference. It's that minus sign that tells us that this is a metric on space-time and not in space. Okay, but in any case, you can check, and if you're bored in this talk, this is a great exercise to check explicitly that indeed for all values of M, in particular, we will consider the case where M is positive, this expression is a spherically symmetric solution of those vacuum Einstein equations. So the Ricci curvature of this expression is equal to 0. Okay. So much later, this metric was understood to describe what's known as a black hole spacetime with exterior region r greater than equal to 2m. So let me try to tell you very quickly what does that mean. So here's sort of a picture. Okay, so you should think of this as a picture where some notion of time goes sort of in this direction, let's say, for now at least, and sort of you know, these directions are the spatial directions. Okay, so the first thing that we notice is that if I look at this expression, okay, here, and I look at r equals 2m, then something very, very funny happens. So if I look at this coefficient of the metric, this seems to blow up. Okay? And this confused many, many people, many, many great mathematicians for many, many years, even though in some sense a posteriori, the resolution of this issue was not difficult. So the point is that it turns out that these coordinates in which this solution was originally described, as coordinates, they degenerate when r equals 2m, but you can change coordinates, and I won't give you the explicit form of the change here, so that the metric actually extends beyond r equals 2m inside this cylinder in space-time. Now, how should we visualize a Lorentzian metric? How do we understand a little bit about the underlying geometry of an expression like this? Well, the thing to remember in Lorentzian geometry, as opposed to Riemannian geometry, is that at every point, okay, we can associate in the tangent space of our manifold a cone, okay? And it's the cone of vectors which have zero length with respect to the Lorentzian metric, okay? So at every point here, here's a point in spacetime, we can draw a cone, okay? So this in reality is a cone in the tangent space, but we'll superimpose it sort of locally on the spacetime itself, okay? And this corresponds to the vectors of zero length. So what's the physical interpretation of that? Well, if I have a curve which is tangent to such a cone, okay, then that represents the trajectory of a light ray in spacetime. On the other hand, massive observers, they are required to remain on curves which are everywhere tangent to vectors which are inside the cone, okay? So what you should think is that this presence of a cone at every point is the thing that enforces the sort of kinematic constraint in relativity that no signal or no observer can travel faster than the speed of light, okay? So at every point there's a cone, and by looking at how these cones are sort of turning, we can try to understand the geometry. So, all right, so what I've drawn here on this slide are the cones in the Schwarzschild geometry. And what you see is the following. When you're very far away, okay, so this and this you should think is very far away, then the cones are upright, just like in Minkowski space. So these are the standard light cones of Minkowski space, if you sort of are familiar with space-time diagrams that we often sort of learn about in a course on special relativity. But as you move inwards, okay, as you move towards r equals 2m, where this m is this parameter, this mass parameter of the Schwarzschild metric, the cones start to turn in. Okay, so you see them, they're turning in. They're turning in. And suddenly at r equals 2m, the cones are tangent to this hypersurface. So what was happening here in this expression, originally it was thought that something was singular here, something was blowing up, but that was just a coordinate issue. What's actually happening, the non-trivial thing that's happening, is that the light cones become tangent to the surface. And if you go a little bit more in, they're turned completely over. So what does this mean? What sort of manifestations does this have? Well, let's consider two observers, okay? So we have the blue observer here, all right? And we have the purple observer, okay? So note that these trajectories in space-time, they have the property that the tangent is everywhere inside the cone. So these are, if you want, these are admissible trajectories of a test particle in general relativity. Okay, so we'll call this observer the wise observer, and we'll call this observer the reckless observer. Okay, so the point is the following: that the trajectory of the wise observer can be extended for all time. Okay, and okay, it doesn't fit in my slide, but you should imagine this trajectory continues for forever and forever. The reckless observer in finite time crosses this r equals 2m. Okay, so now let's look at the trajectories that the reckless observer can send. Okay, so here's an example of a signal that the reckless observer can send. So signals are required, you know, best case scenario, they travel exactly tangent to these light cones. So here's an example of a signal. Okay, and later on, maybe there's a signal that goes like this and meets this observer much later. But when the reckless observer crosses r equals 2m, then any signal that the observer sends, okay, at best can remain tangent to r equals 2, okay? Because the light cones have turned. And now, okay, if the observer goes further in, then the light cone has turned completely. So all signals are being sent to smaller values of r. So in particular, any space-time point, which is in this region here, okay, has the property that any signal it tries to send is always being sent to smaller values of r. So in particular, no signals arising from this region here of space-time can ever leave it. Okay, so in particular, they cannot go to to wise observers like this one over here, far away. So we call this region of space-time a black hole region, and all it means is that it's some region of space-time that cannot communicate to faraway observers. Okay? So it's not something so strange or difficult at the end of the day. It's a purely geometric notion, which should be very appealing to all of us mathematicians. Okay, it's just some region of your manifold of space-time that, because of the geometry of these cones, cannot communicate to sort of faraway observers. Okay, so to in particular, but more generally to observers outside this region. Okay, so so that's the black hole notion, and we'll return to it very soon. So the last aspect of the crash course in general relativity is a few words about the Koshy problem, because, as I said initially, there are two ways to think about the Einstein equations. You can think about it as a geometric relation, the statement that some sort of curvature is equal to 0. But you can also think of that relation as a PDE, because, of course, curvature is whatever it is. It's some complicated expression in derivatives of the metric. It's up to second derivatives of the metric. And I already told you, and we've even observed, that curvature propagates in a wave-like manner. And that's a manifestation of the fact that this fundamental set of equations is of hyperbolic character. Okay. And again, if one wants to make a comparison with other problems in mathematics coming from geometry that maybe people are familiar with, in Riemannian geometry, when you write natural sort of partial differential equations connected to the geometry, these typically are elliptic or maybe parabolic. Okay, and the reason is that the natural differential operators associated to a Riemannian metric are elliptic. Well, in Lorentzian geometry, everything is formally the same. Every sort of expression takes formally the same form, except there's a minus sign. Okay, and we all know that what happens when you take the Laplacian and you make one of the coordinates, you put a minus sign in front of the derivatives, well, you get the wave operator. Well, so a similar thing has happened here in Lorentzian geometry. So it turns out that the equation Ricci curvature equals 0 is secretly a nonlinear system of hyperbolic equations. And as such, what you expect is you have a well-posed initial value problem, because we all know when we learn about the wave equation that the natural problem to pose is the initial value. Okay, so this understanding that general relativity can be phrased as an initial value problem was a big achievement of Yvonne Choquet-Brouillard from 1952. And what she proved is that, just like for the equations of Newtonian dynamics, in general relativity, appropriate initial data uniquely determine a solution of these Einstein vacuum equations, the equations that Einstein wrote down back in 1915, at least for sufficiently small, for a sufficiently short time. Okay. So, so even though general relativity is a sort of new, exciting, sort of very modern theory, at the same time, it is quintessentially classical, okay? In the sense that, just like in good old Newtonian dynamics, there's a notion of initial data, and initial data determine uniquely a solution of the equations, at least for short time. Okay, so what's the significance of this theory, of this theorem? This theorem is the statement that essentially tells us that we can understand general relativity dynamically, and we can ask dynamic questions. So, so in the rest of the talk, I will turn to the study of dynamical questions concerning black holes. Okay, and in some sense, the first such dynamic question that makes sense to study is the so-called problem of stability. Okay, so so let's try to understand what is the problem of stability. So let's recall we have the Schwarzschild solution. This is an explicit solution of the Einstein equations. We have a Cauchy problem. We have a framework to understand dynamics of the theory. The first question we can ask about the Schwarzschild solution is it stable? So this is a recent theorem joined with Gustav Holzhegel, Igor Rodnyansky, and Martin Taylor. So the basic statement of the theorem is the following, that the Schwarzschild family of solutions, the solutions that I wrote down before, the sort of original non-trivial solutions of the vacuum Einstein equation, are indeed asymptotically stable as a solution to the Koshy problem of the Einstein equations for the full expected set of perturbations without symmetry. So let me just say a few words. What does stability mean in the context of the Koshy problem? Well, it means exactly what you might think it means, namely, this is an explicit solution. So in particular, you can think of it as being the unique solution of the Koshy problem corresponding to some particular initial data set. Okay, so in the language of the theorem of Yvonne Choquebras, this is, you can think of this metric as the maximal Cauchy development of some particular initial data set. Okay, so the stability problem is we wiggle ever so slightly the initial data. Okay, we take a general sort of initial data set close to the initial data that led to this. We solve the Einstein equations. Yvonne Choquebras' theorem says that we can, there is a unique solution. And so the stability question is, well, what happens to it? What does it do? Does this solution remain close to the Schwarzschild metric? Does the solution converge back in a suitable sense of that word to the Schwarzschild metric as time goes to infinity? Okay, so that latter issue is the issue of asymptotic stability. Okay, and the theorem says that this is true for, well, this is a funny phrase, which I'll explain in just a second. So let me say it like this. It's true for all perturbations for which it ought to be true. And I'll get back to that in just a second. Okay. All right. So let me just tell you, first of all, very, very quickly, a few words about the prehistory of this problem. So actually, the study of this problem goes back to my academic grandfather, Johnny Wheeler. So he wrote a paper already in 1957 about the so-called mode stability of Schwarzschild. So this is a sort of very restricted type statement in linear theory. And maybe I'll also highlight a work from maybe 7 years ago now. So together with Holzhegel and Rodnyansky, we proved the full linear stability of this solution. And this sort of opened the way to sort of general linear and nonlinear stability results for black holes. And there's been a lot of further developments in this subject since then, which I'll discuss a little bit now. Okay, so of course, I should say that somehow these nonlinear stability results are longish and quite technical, but there is a sense in which, you know, the fundamental difficulty of showing them is already at the linear level. So already showing somehow the linear stability of these solutions, that's to say you linearize these complicated equations and you try to understand sort of stability at the linearized level, that's already complicated. And then you should think that the nonlinear stability results, well, using a lot of technology from nonlinear analysis, you can upgrade a linear result to a nonlinear. That's sort of the very, very general terms how it goes. So I can't really give a sort of justice to all the things that go into this, these type of proofs, but maybe I can just say a little bit about two aspects of the proof of such a result, just so that we can see a little bit the geometry of these black hole solutions. One nice aspect of this problem is there's a very close relation between geometry, if you want, physics, and analysis. Okay, so two difficulties that you have to come to terms with in order to prove this type of thing is the issue of the so-called redshift and the issue of trapping. Okay, so let me try to give you a little taste for these issues, what they mean in the context of the Schwarzschild geometry. So again, this is the Schwarzschild geometry. So remember, this here is the black hole region. This is the region from which signals cannot leave, and we saw this turning of the cones. Okay, and so I want us to remember our two observers. So before we had the reckless observer. So this is the reckless observer, and we had the wise observer. But today, there will be no wise observers. There'll just be two reckless observers. Okay, so this is two reckless observers. Okay, entering into the black hole region at later times. Okay, so the first reckless observer enters the black hole region at this time, and the second reckless observer enters at a later time. Okay, so by the way, this surface r equals 2m is known as the event horizon. Okay, so these are the times when the two observers cross the event horizon. Okay, so now imagine that, and I don't know the good color to do this. I hope this is visible. So imagine that the first reckless observer is sending a signal to the second one. Okay, maybe that isn't so visible, so I'm going to have to do it like this. So suppose this observer is sending a signal to the other one. You can imagine that the signal might travel on a trajectory like this, okay, and sends a signal later. So what turns out to be the case, okay, is if you look at the frequency at which this signal is being sent out by this observer, and the frequency by which the signal is being received by the other reckless observer, then it turns out that that frequency is shifted to the red. That's to say that the signal becomes more infrequent, okay? And the reason is exactly because of this spreading out of the light rays that you see here. Okay? And in fact, if you send this time to infinity, then this frequency as sort of measured by this observer is sent infinitely to the red. That's to say the frequency of waves generated by this observer, okay, is infinitely damped. So this is the famous sort of redshift effect associated to the event horizon. And it turns out that this is a good effect in general relativity. This is in particular one of the things that ensures that this horizon is a stable feature. Okay, that sort of perturbations generated near this horizon, okay, don't sort of destroy the horizon. So one aspect of these proofs is capturing this sort of redshift effect, which again, you can describe purely using the geometry of cones, okay, capturing it in analysis. So, so there's another very interesting effect, which is more difficult to visualize from the cones as I've drawn them, but I'll make an attempt. And this is the issue of trapping. Okay, so let's forget about these observers. Okay, let's try to understand what trapping is. So, okay, this will need a little more visualization, but again, I think we can maybe do it. So let's fix, let's say, this space-time point here. So you might notice that if I go in the radial direction in a null direction, then I'm going to enter the black hole region. This is a light ray. Okay, and you might believe me that if I go in a radial direction in the outward region, okay, then I'm going to escape from the black hole. Okay, so you know, light going radially out will escape from the black hole. Okay, so now imagine that I sweep out the directions of this cone. Okay, so I look at light going in all directions, sort of a family of directions sweeping out from here to here. Turns out that there's a critical light ray, okay, that will neither fall into the black hole nor go out to infinity. Okay, so actually what this null ray will do is it will circle. It's very hard to draw on this type of picture. It will circle around the black hole. Okay, so what this is the following. It's sort of like a planet orbiting around the black hole, except it's not a massive object, it's a light ray. Okay, so this is what's called a photon orbit. Okay, and it's very easy to convince yourself, even without computation, that such things exist in the Schwarzheim. So what does that mean about sort of stability? Well, again, if you think that in the high frequency limit, okay, photon orbits in the sort of geometric optics approximation, they are a high frequency limit of waves. And the Einstein equations themselves are of wave type. So what that means is that in the analysis of the Einstein equations, you see this sort of trapped behavior in some sort of high frequency limit. And well, if there are these photons that stay around, they don't fall into the black hole, they don't go to infinity, then you might worry that solutions of the Einstein equation will not settle down. There'll be something trapped always, so they will not settle back down to a stationary solution. So these type of objects, naively at least, they seem to be an obstacle for proving stability. So what saves the day is something related to the picture that I drew, namely, yes, there are these very exceptional orbits, but they are exceptional. That's to say, if I look at nearby null geodesics, so if I look at nearby photon trajectories, then either they will go out to infinity or they will fall into the black hole. So these photon orbits are inherently unstable. And capturing that fact well in the analysis is an essential point of showing the stability properties of the spacetimes themselves. Okay, so this, I hope, gives you a taste of some of the aspects of the stability problem. In fact, these already enter at the linear level. Okay, so now I'm going to tell you why this theorem says for the full expected set of perturbations, Schwarzschild is asymptotically stable, and not for all perturbations. So, so the reason is very simple. The Schwarzschild family, this first non-trivial solution of the Einstein vacuum equations to be discovered, was secretly a one-parameter subfamily of a larger two-parameter family of solutions discovered by Roy Kerr. So the larger two-parameter family of solutions is again explicit. So I've written it in coordinates. These were not exactly the coordinates that Kerr discovered the metric in. Well, there's a little bit of notation here, so it looks complicated, but it's certainly not infinitely complicated. And you certainly can verify a posteriori that this is indeed a solution of the Einstein vacuum equations. Maybe it will take you a little longer than verifying the Schwarzschild metric is, but again, if you're bored in this talk, feel free to compute the Ricci curvature of this expression here and convince yourself that it vanishes. So sort of interesting that this metric took a long time to be discovered. You see, this metric, unlike the Schwarzschild metric, this metric is not spherically symmetric. So you can't just impose the symmetry and hope that you'll be able to find an explicit solution just, you know, by solving some ODE. This metric is only axisymmetric and stationary. So it only has two, you know, killing vector field symmetries. So it's actually rather remarkable that you can still find an explicit solution. It's sort of, you don't have enough symmetry to justify it. And somehow the reason that this exists as an explicit solution is really related to some hidden symmetry that the object possesses. And the story of its discovery is quite remarkable because one had to make a sort of fortuitous choice of ansatz in order to find it. So there's a reason why this was only discovered in 1963, and sort of these medals that Roy Kerr is wearing in this picture are well deserved. In any case, so this is a two-parameter family of stationary solutions. Okay, the parameters are A and M. You should think of A as a rotation parameter. It's sort of angular momentum per unit mass. And again, this describes a black hole spacetime if the parameters satisfy this relationship, this inequality. And Schwarzschild is simply the subfamily where A equals 0. So the existence of this family basically says that, you know, in particular, you can perturb the Schwarzschild initial delta to a member of this family. And those are stationary solutions. So those are not going to settle back down to Schwarzschild because these are stationary. So this sort of tells you that there are some perturbations of Schwarzschild, okay, which do not settle back down to Schwarzschild, okay? And you can think of Schwarzschild as a codimension 1 subfamily, okay? So what our theorem actually says is that in the whole moduli space of solutions, okay, there is exactly a, let me call it codimension 1 subfamily of initial data, okay, for which the solution is asymptotically stable. Okay, and the presence of the Kerr family tells you, in essence, that that result is sharp. Okay, so so another way of saying this theorem is that you have asymptotic stability of the Schwarzschild family modulo the Kerr solution. Okay, so okay, so that's that theorem. But of course, we're also interested in understanding the stability of the Kerr family more generally. And it turns out that there's an additional feature of the Kerr family, which sort of, in some sense, is the reason why proving things about Kerr becomes more difficult. And this feature is the so-called phenomenon of superradiance. So let me just try to give you a little taste of what this phenomenon of superradiance is. So at first glance, the geometry of the Kerr family is very similar, very analogous to that of Schwarzschild. So if I just draw the cones, okay, then again, I have this feature that the cones very far away are upright. As I go in, the cones turn inward. And there's some critical value of R, which is actually now not 2m, but what I call R plus. R plus is, if you're paying attention to this slide, it's the roots of the, this quadratic expression delta. Okay, it doesn't matter what it is. At this critical value R equals R plus, the cones are tangent to R equals R plus. Okay, and then if you go further in, they've turned in. So again, just like in Schwarzschild, this region here is a black hole. So what's the big difference between Schwarzschild and Kerr, apart from the sort of the slightly less symmetry? Well, the big difference is the following. So remember, these solutions are stationary. So you should think stationary means they don't depend on time. But the geometric way of saying they don't depend on time is to say that there's some vector. This is the vector, okay, at each point. Okay, there's some vector, all right, which is a killing symmetry of the metric. Okay, so this is the infinitesimal generator of a one-parameter family of symmetries of the metric. Okay, so when you're far away, that symmetry is indeed time-like. It's pointing inside the cone. Okay, but a remarkable thing happens in the Kerr family, which is that if you go close enough to the black hole, this symmetry is actually not pointing into the cone. It's pointing outside of the cone. So what does that mean? Well, one very important way of sort of understanding wave equations is by showing what are called energy estimates. All right, and energy estimate basically means that we consider a symmetry of the underlying metric, and we construct a conserved quantity for waves, which is related to the symmetry. Actually, the reason that you can do this goes back to Noether. This is sort of related to the famous Noether's theorem. So in particular, what you try to do is you try to sort of construct some conserved quantity associated to sort of a hypersurface in spacetime, and show that some sort of energy associated to this conserved quantity sort of on this hypersurface, and then similar quantity on a later hypersurface. You want to show that the later quantity is controlled by the previous quantity. So the problem with this situation, where you see that the symmetry, the killing field, is pointing outside of the cone, is the following. The reason that energy is positive has to do geometrically with the fact that, the symmetry that we use to define energy is pointing in the time direction. So when we consider energies with respect to symmetries that are not pointing in the time direction, then the energy density is no longer positive. So the usual conservation of energy that we're used to holding, and that's very important in showing stability, okay, is no longer a positive quantity. And if energy is not a positive quantity, then its conservation does not control the solution, because the total energy can be bounded, but it can be bounded because somewhere it's very positive and somewhere it's very negative. So this is a phenomenon that happens in Kerr, and you should think that the strength of superradiance grows as your rotation parameter grows. Okay, so it turns out that in the case where the rotation parameter is very small, essentially because superradiance, whatever it is, it's controlled by a small parameter, you can perturb the Schwarzschild analysis. And exactly how to do this in linear theory was unlocked in these two independent works that I show here. And well, there's been further work in the full linear theory, and even some recent papers on the full nonlinear problem in the sort of essentially perturbed Schwarzschild case. So in the case where this A parameter is very, very small. But the real interesting case to understand for Kerr is somehow the full sub-extremal case of parameters, the case where A is a general sort of value less than M. And here the sort of the linear analysis that tells you whether or not you should expect the Kerr black hole to be stable is much more subtle. And it's only very, very recently, and I really mean very, very recently, if you look at the sort of dates of some of these papers, been unlocked in a series of papers. Okay, so and one of the big difficulties here is precisely quantifying this issue of superradiance and showing that superradiance does not kill you in the Kerr geometry. So, in view of these works, so these particular works of Schleppentoch, Rothman, and Teixeira da Costa, one could hope that a complete proof of nonlinear stability of the Kerr family in the full sub-extremal case will be available in the near future. Okay, so this gives you a taste of the most simple dynamical problem you might want to study in general relativity, namely the problem of stability. But of course, it's even more exciting if you can show instability results about spacetimes. So the next thing I want to talk about is instability. And it turns out that we can already see instability, surprisingly, in the Kerr family. Well, how is that so? So you may remember when I talked about the Kerr family, I told you that this metric represents a black hole spacetime in the range of parameters when this rotation is less than equal to this mass parameter m. Okay, and you may have, if you were paying attention, you may have noticed that when I talked about stability, I always restricted to the sub-extremal case. That's to say, the case where we have strict inequality. So the case where we have equality, okay, this is the so-called extremal case, is interesting because again, it describes a black hole, but somehow it is the case of maximal rotation. So remarkably, around 10 years ago, it was discovered that all sort of extremal black holes, so all black holes that share a certain geometric property with extremal Kerr, suffer from a very elementary instability associated to the event horizon, associated to the boundary of the black hole region. So this is the famous Aretakis instability. And the theorem basically, and it's a very general theorem on black hole backgrounds, says the following. Linear waves, so any sort of linear wave equation in the exterior of an extremal black hole will be subject to non-decay of first derivatives and polynomial growth of higher derivatives. So let me just say a little bit why this happens. So this effect happens exactly because the redshift that I talked about previously in the extremal case degenerates. So if this is now what you see in front of is the geometry of extremal Kerr, and I go back to these two reckless observers. So here's one, and here's the other. So two observers which both cross the event horizon. And I look at the signals sent by the first reckless observer to the second. Then to first order at horizon crossing time, okay, we don't have any spreading out of the signal in the extremal case. So, so that nice effect that led to a dampening of the frequency of waves emitted by this observer as received by that observer, it degenerates in the extremal case. And it's actually this degeneration which is at sort of at the origin of this Aretakis instability. So one thing that's quite remarkable is the extremal black holes have been studied in the physics literature intensely because they're very, very important astrophysically. So for various reasons, it's believed that many astrophysical black holes are very near to this extremal limit. But extremal black holes are also of great interest in high energy physics because, again, for very different reasons, they seem to come up in supersymmetry and in string theory. Nonetheless, this very elementary instability discovered by Aretakis was not discovered in the physics literature, and was only discovered by sort of actual rigorous mathematical analysis. So I think that's actually quite interesting. Okay, so it turns out that in the specific case of extremal Kerr, there are even worse instabilities than the Aretakis instability. And very, very recently, Gajic has discovered that if we look at non-axisymmetric perturbations of extremal Kerr, then not only do first derivatives of wave equations not decay on the horizon, but they actually grow polynomially, already first derivatives of perturbations. And in any case, this sort of result tells you that nonlinear stability of extremal Kerr cannot hold, at least in the form that it holds for Schwarzschild, even if we restrict to the finite codimension set of perturbations which preserve the finite parameters. In any case, so this effect, which is sort of behind this recent result of Gajic, is maybe more tricky to explain. What's going on here is that this problem of photon orbits is somehow meeting the horizon. So what I mean is the following: in the Schwarzschild case and in the sub-extremal Kerr case, then if you're sufficiently close to the horizon, okay, then there are no photon orbits there. So there are no photon orbits here that stay in this region for all time. Okay, if you're sufficiently close to the horizon, okay, if you want to stay in this region, you actually have to fall into the black hole. But in the extremal case, there are actually photon orbits arbitrarily close to the horizon. And it's that interaction of those photon orbits which causes this sort of even worse instability here. So it's really an open problem to understand exactly what happens for extremal black holes. There's an instability. One might hope that it's a weak instability. So at some coarse-grained level, there's still some sort of stability. But even at the linear level, in some sense, it's completely open to understand the sharp behavior of waves on these kinds of backgrounds. So it's very easy in the subject to arrive at problems which sort of very easy to state, but are still not understood at all. Okay. So as a very short aside, let me just say the following words. So one of the reasons that the study of extremal black holes, the sort of correct mathematical study of extremal black holes was delayed, was there was a feeling in the literature that such extremal black holes, even though you can write down that metric, solutions of that type would never form dynamically in gravitational collapse if you started from a sub-extremal black hole. And in fact, there was a principle which was known as the third law of black hole thermodynamics, which basically said that exactly what I just said, namely, it's impossible to create a extremal black hole starting from a non-extremal black hole dynamically as a solution of the Einstein equations. Okay. Remember, this black hole here is always exactly extremal. Okay. So the statement would be, if you start with something sub-extremal, you could never in finite time arrive at something extremal. So somehow, if you believe this statement, then maybe the conclusion would be that, okay, there is this instability, but if we agree that the initial state of the universe is never near this extremal black hole, then you can never arrive at that dynamically, and thus you don't have to worry about this instability. But actually, recently it was proven by Kerr and Unger that no, there are actually sub-extremal black holes that become extremal in finite time dynamically, starting from completely regular initial data. So in particular, this third law of black hole thermodynamics is just false in general relativity. And this, again, is a sort of a surprising fact, because this third law basically appears in most textbooks on black hole physics, but it's in fact incorrect. So extremal black holes do form dynamically, and we do have to think about their precise stability / instability properties, and it's a really delicate problem in analysis, which maybe some member of the audience might want to study in the future. Okay, I think there's a lot to be done for that. Okay, so in the short remaining time, let me talk just a little bit about the final dynamic problem that one might want to consider, which is the problem of singularity. So let's go back to Schwarzschild. So this is another picture of the Schwarzschild spacetime that if you're a relativist, you have to start getting used to. So remember, when I was drawing the Schwarzschild spacetime before, I was drawing the cones, and I was drawing the cones turning. Okay. So that's sort of the first, most naive picture that you want to have. But a more sophisticated geometric picture is the following. So let me suppress the 2 dimensions. So that's to say, I suppress this. This is maybe too big. So I suppress 2 dimensions. So my cones are just now. You see, my cones are now, they look like this. Okay. And now I do a coordinate transformation to make my cones upright. Okay. And it turns out that you can do that in 2 dimensions. That's sort of a version of the uniformization theorem that many of you know from, 2-dimensional Riemannian geometry or complex analysis. Okay. And so this is sort of a canonical way to depict spacetimes. So in these depictions, which are called Penrose diagrams, okay, the cones are always upright. So if I have a point in my spacetime, okay, then the future cone is always this, and the past cone is always that. Okay, so these type of depictions of spacetimes are what are known as Penrose diagrams, and well, the Schwarzschild spacetime has the depiction that you see here, and well, it takes a little time to get used to reading these, so you'll have to maybe believe some of the things that I say, but in any case, it's good to get a little taste of this already. So this spacetime has a boundary at infinity, okay, and the boundary at infinity is exactly this and this, and what you can read from this picture is that the points of spacetime that can send signals to infinity are precisely these points here, because these are just the signals going off to infinity, and these points here. So in this depiction, you can read off immediately from the picture that this region here is the black hole. Okay, so all right. so why is this picture useful? This picture is useful because now we see what is the boundary of the black hole region to the future, and we see that the boundary to the future is this r equals 0 curve. Okay, so I want us to contrast this with what we were drawing previously. Go back here. So if you noticed what we were drawing previously, okay, it looked like the boundary of the black hole region was a curve that went like this. But now we see that when we do this geometric depiction of the black hole region, okay, we see that the curve actually goes like this. So what is the significance of that fact? Well, the significance is that this boundary here, this singularity, okay, is space-like. And what that means is that two observers falling onto this singularity, okay, they cannot communicate with each other when they're sufficiently close. So if this observer is very close to this singularity, and this observer is very close, then no matter how they try to communicate, they can no longer talk to each other. So, so this fact was first noticed by J.L. Singh in around 1950. And moreover, J.L. Singh posed the following question. Okay, so this is a singularity, so you can compute the curvature blows up here. Okay, but is it conceivable that test particles should be able to travel through this singularity? And well, he actually thought the answer was yes. It turns out that the answer is no. You can do a little geometric computation, and what you can show is that any observer falling into this singularity is torn apart by tidal deformations. Well, what does that mean geometrically? It simply means the following. If I think of my observer as modeled by hands and legs, so these are two hands and legs, you can think of these as Jacobi fields. And so you can ask yourself, how do these Jacobi fields propagate along this geodesic? And well, what was shown in Misner-Thorne and Wheeler is, well, here is the observer, and think of the hands and legs as Jacobi fields. As the observer falls along this geodesic, then the hands and legs are infinitely stretched out or infinitely compressed depending on their orientation. And so what this means is that the observer is destroyed. So a natural question in general relativity about singularities is the following. Is it true that in black holes, there is always a space-like singularity? And is it true that all observers falling into black holes are destroyed in this way? Okay. So this is true in the Schwarzschild spacetime, but suppose now we perturb Schwarzschild, like in the previous theorems, but we don't look in the outside of the black hole, we look inside the black hole. Is it still true that observers are destroyed in this way? Okay, and is it true that sort of the geometric character of the singularity is space-like? So I don't really have much time to say much more, so let me just say the following. The conjecture that all observers falling into black holes are destroyed is known as the strong cosmic censorship conjecture. And this is a conjecture that first was posed by Roger Penrose, and it actually was posed because the situation in the Schwarzschild example is very different from the situation in the Kerr example, and I don't have time to sort of discuss that more. Now, the conjecture that the singular boundary of a general black hole is always space-like is something that one could call the space-like singularity conjecture. Okay, and again, it's essentially also something posed originally by Roger Penrose. So So it turns out that actually both of these conjectures are false, as I've stated them. So this is a theorem of mine together with Jonathan Luke. But some revised version of these conjectures may yet be true. And so an important problem in general relativity concerning singularities, and I'll just skip right to the end, is to understand what version of strong cosmic censorship is true, namely, what is the sharp description of the singular boundary of space-time for general perturbations of our black hole metrics. Okay, so let me end, since I've gone over time, with some goals for the future. So first of all, we would like very much to extend our understanding of nonlinear stability of black holes to extremal and near extremal black holes, in particular, to understand to what extent are they unstable, and if there's any sort of stability that still holds, compatible with the type of instabilities that we already know exist. So this is a very important problem from the point of view of astrophysics. To prove or disprove the revised space-like singularity conjecture, I told you that it is not the case that singularities are in general space-like, but there's some revised version that may be the case, and we very much want to prove or disprove that. And finally, to prove or disprove the revised version of strong cosmic censorship, namely sort of the revised version of the statement that observers falling into black holes are destroyed. Okay, so that's goals for the future. So maybe I'll end with that. And if anyone has any questions, I'm happy to entertain. Thank you.
Thanks, Mihalis. Let me thank you for on behalf of everybody. Are there any questions?
I have a question.
Yes.
Mihalis, we met 15 years ago.
Oh, I remember, of course.
I wasn't sure whether it was you, so I checked your CV. It was you. You have changed a little bit.
A little bit.
I have
but
an
of
unfair
course,
question for you. I have an unfair question for you. I wouldn't ask it to anybody.
Okay.
The question is the following. After your talk in Istanbul, and I try to follow these things a little bit, read papers, but when I told about these problems to my physicist friends, about the koshy problem, etc., they said it is not the right question to ask. I don't know why they said that, because I'm not a person in relativity theory. Can you say something about how the physicists are reacting to these the studies that you have been doing with this wonderful group at Princeton?
No, I mean, I think, of course, there are many problems in the subject, and I should say at the onset that these are not the only ones, but these problems are now actually studied quite a bit in the physics community. And in fact, well, I didn't talk more specifically about this whole issue of strong cosmic censorship, but one thing that's very interesting, and maybe I'll just say 2 words, is that what turns out to it seems that the right statement in the context of strong cosmic censorship is the statement that the singular boundary of space-time should be of the following form, that the metric extends continuously, but first derivatives of the metric fail to be locally square integrable. So to say it in another way, in mathematical language, that the metric is not in the Sobolev space H1. Okay. So you might think that is the last type of statement that sort of people in physics would care about, study, whatever. I mean, it's a statement that involves, Sobolev regularity or whatever. But I can tell you that sort of the analog of this statement for positive cosmological constant, which sort of, you can also make this conjecture. Well, in the last 5 years, there have been maybe 100 papers in the physics literature, and all these papers, I mean, not only do they sort of adopt this formulation, namely that the correct formulation is this revised formulation that came out of mathematics in the sort of concerning inextendability in the Sobolev space H1, but they do it, you know, as if it was the most obvious thing to do, in the sense that, you know, it's not only that it's adopted, but it's, so in any case, I mean, I think that, I don't think that there's sort of fundamental disagreement sort of in general in theoretical physics, but between, let's say, theoretical physics, mathematics, astrophysics, as to sort of what kinds of questions one is interested in. I think, on the contrary, I would say that one of the nice things in this field is that at the end of the day, you know, we are all interested in the same question. I think mathematics is typically more focused, and somehow one difference that I see, to entertain your question just a little bit more, is that you know, the fact that mathematics is something unchanging, and that, you know, mathematically difficult problems, they remain difficult. They, you know, progress on them is slow, but progress that has been achieved is permanent. It keeps us a little more focused, and sometimes people in physics, you know, all these problems arose, after all, from physics and from the physics literature originally, but very often people have to be reminded of the right problems, because in physics people you know, are less focused sometimes. So, but anyway, I wouldn't say that there's a big philosophical difference. It's just that, you know, the time scale of mathematics is a little bit different, and so we have to stick also to the most fundamental questions.
Okay, thank you. Nice to hear from you again.
Likewise.
Mihalis, thanks for your talk. Unfortunately, I need to run the thesis defense, so Sinan will take over, okay?
Okay.
Yeah,
Bye.
thanks for the talk.
Thank you very much for having me.
Okay, we have two raised hands. Whoever wants to go first, maybe.
Well, you give word. You are
Okay.
the moderator.
Okay, so I'll please go ahead.
Okay. Well, I am a physicist who has in the past worked on the weak censorship conjecture, which you didn't mention. Of course, one cannot work on it kind of in general, but one works on it in certain contexts that one sets up. I've seen papers in literature that set up a context and then use the second law of black hole thermodynamics to prove that the weak cosmic censorship holds in that context. To me, that sounds like a tautology. What do you think about it? I mean, the weak cosmic censorship conjecture is almost identical to the second law of black hole thermodynamics, I think. What do you think about that?
Well, I mean, I certainly agree that, okay, one will not learn anything sort of about weak cosmic censorship by, you know, sort of assuming whatever law of black hole thermodynamics. So this, I certainly agree. I certainly agree, by the way, that it's a wonderful problem, and I regret not being able to discuss that problem also, because it's also a problem that I'm very interested in. And it's also, so just to give some of the audience maybe some context, so the problem of weak cosmic censorship is the question of whether generically all singularities are hidden inside black holes. So that's one way of sort of formulating it. So the singularities that I briefly discussed, the singularity inside the Schwarzheim solution, as we saw, whatever it is, however bad it is, it's hidden inside the black hole. So it's only relevant to the reckless observers, the observers that decide to fall into black holes. So a very important question is whether all singularities in general relativity, or at least generically, possibly for some set of measure zero in the moduli space of initial data, this might not be the case, but for generic initial data, whether it's the case that if you have singularity, it's necessarily. So the conjecture that that's the case, that's weak cosmos. Yeah, no, I mean, it's a very important problem. There has been some mathematical work, but as you said, sort of the state of current understanding is still very primitive, and so in particular, the mathematical work that exists is restricted to work under symmetry. So the best results that are available about weak cosmic censorship are results, for instance, in the context of the Einstein scalar field system under spherical symmetry. This is maybe the best results in the subject. This is very classical work now of Christodoulou, proven over maybe 30 years. And the statement is that the conjecture is true in that model, restricted to spherical symmetry. But that's
what we've been trying to do is perturb extremal or near extremal black holes with sort of, I mean, in Gedanken experiments with tailored fields, and it seems like fermionic fields seem to trick. But so here I shut up.
Well, that's also, I mean, I think, and this is not unrelated to, by the way, what I just mentioned about the third law of black hole thermodynamics, and it's the fact that it's not true. I think it is interesting to look at this problem near extremality. I think, in particular, I suspect that a lot of, as you having worked on this, you probably know better than me that there's a lot of papers on that, and there's a lot of confusion about that. I think a lot of this will be cleared up in the years to come. I think there's some very interesting behavior precisely at the extremal threshold, not unrelated also to the instabilities that I discussed earlier in the talk. I think it's an interesting direction. So definitely, I'm interested in that problem. Yeah.
Okay, we have one more raised hand. If the question is Shahin Sheikh Jabbari, please go ahead.
Hi, Mihalis. Good to see you again.
Yeah.
Thank you very much for the interesting talk. Actually, I have 3 or 4 questions. Let me start with the one that we were just discussing. What do you think about the proof of the third law given by Werner Israel in his 1986 paper? You may remember that paper.
Yes. In fact, I do, and it's a very interesting story, exactly because if I go back to this theorem. So yes, there was a paper by Werner Israel which claimed to prove a version of the third law, and I'm telling you that there's a theorem that tells you that the third law is not true. So what's going on? So it turns out that theorem. Okay, the paper is not written sort of very formally, and actually there was an implicit and not appropriate assumption in the theorem that was implicit, was not stated, and that's why so that's what's going on in that paper. So and it's very simple. I can say very simply that sort of that argument was making the implicit assumption that what's called the outermost apparent horizon is connected. And it's never said, but that was being used in the proof. But sort of in a dynamic black hole, even if the whole spacetime is completely smooth, in general, the dynamic, the outermost apparent horizon will not necessarily be connected. And the reason is simply because, the level set of a smooth function can jump. There's nothing irregular about a level set of a smooth function jumping. And it's very interesting how, and by the way, this is in some sense in other contexts, it's quite familiar to people, numerical people who study, let's say, the evolutions of black holes, that the outermost dynamical horizon can jump. So that was actually the issue in that paper, and this is discussed in the paper of Kele and Unger. This is discussed. So that's the origin of that, and somehow that was not. It seems it was not.
So
I mean, it seems that in fact it's quite clear in what he says, because in that paper, I mean, he makes a big point of saying that there are counterexamples to the third law where you have singular matter fields. Okay, and the whole point of his paper is to say that, well, if you don't have singular matter fields, then you'll have third law. So that the reason that sort of you have counterexamples to third law if you have singular matter fields, if you have violations of the energy conditions, but if you impose that the matter fields be regular, that sort of the energy condition hold, etc., you should not have violation. That's somehow the point of his paper. And in the discussion of his paper, he gives the examples of the singular matter fields. Those examples have a disconnected horizon, and he seems to say that the reason that the horizon is disconnected is because of the singularity of the matter fields. So it seems that incorrectly his expectation implicit was that somehow these two things were connected, but finally they are not. So you can have completely regular examples. They form. So this, in the case of this paper, you're just looking at the spherically symmetric collapse of a charged scalar field. Everything is completely regular, and in finite time it becomes exactly extremal, having been exactly sub-extremal at some earlier time. And there's there's nothing irregular, but the outermost apparent horizon jumps. So that it's just the statement that there's nothing wrong with a level set of some smooth function jumping. That's finally what's going on. It is pretty amazing that sort of this was not.
So let me ask two other questions which are related. So you mentioned about the possible instability of the Artakis instability of the extremal black holes. Where does it end up with? So if the extremal black hole is decaying, what's the end of the evolution?
Well, I mean, this is exactly what I have no idea, and I'd love to know, and I think it's a great problem. I mean, it's sort of let's say the best case scenario with this sort of behavior is simply that, okay, in the full nonlinear theory, what this means is that you'll have growth, you'll have certain derivatives of the metric, so in particular the curvature even along the horizon perhaps will blow up asymptotically. But if you take a coarse-grained approach, you don't look at Kerr, you just look at the metric still is approaching extremal black hole. So, the one scenario is that, okay, nothing is from a sort of, if you just look at the metric and you don't look at its derivatives, you have stability. Okay, it's just that, okay, if you look at these dynamic solutions that are, approaching in this way extremality, their derivatives are blowing up, asymptotically, but the metric itself is converging to extremal Kerr. So that's not out of the question. And in some sense, if that's what happens finally, then I'm very confident that will eventually be mathematically proven. But of course, as you said, you might worry that, okay, you have this growth, and then this growth leads you away from the Kerr family, in every sense. And, once you're away from the Kerr family, then, okay, who knows what happens? And yeah, I mean, that would be more exciting if true. But, we really don't know. So yeah, that's
and maybe the extremal Reisner-Nordstrom would have similar instability or growing modes. So maybe that's a simpler setup than extremal Kerr to address the
Yes,
question.
it is, and in fact, it is simpler in the sense that extremal Reisner-Nordstrom is subject to the Arithakis instability, like all extremal black holes, because Arithakis instability is completely general. But it is not subject to these what Gaich calls azimuthal instabilities of extremal Kerr. So extremal Kerr is in some sense more unstable, but these worse instabilities, they are related to this other phenomenon. They are related to the phenomenon of trapping of sort of photon orbits, which are very close to the horizon, which is a phenomenon of specifically of extremal Kerr. Okay, because in extremal Reisner-Nordstrom, in some sense, the trapping is always at r equals 2m, and the horizon is always at r equals m. So there's a distance, even though you're extremal. But in extremal Kerr, you have sort of photon orbits around the black hole, which are as close as you want. That's somehow the source of this extra instability. So I certainly agree that the place to start on this problem is extremal Reisner-Nordstrom, where the situation is simpler. And yeah, I mean, you may conjecture, in fact, I even in the paper we wrote about the nonlinear stability of Schwarzschild, we have a conjecture about the sort of stability of extremal Reisner-Nordstrom, which is sort of basically asserts that indeed, from the coarse grain point of view, it is stable, even though higher derivatives blow up. But okay, we just make this conjecture to write something. I don't know that this conjecture per se, I have no hidden knowledge that this is true or not true. It's just something to focus on and hopefully indeed prove.
Yeah, and another related fact is the uniqueness of the extremal black hole solution. So as you know, the uniqueness theorems can be extended to extremal black holes and has been actually, maybe in 2007 and 2009. By you know these papers. So I was just wondering whether this instability and that uniqueness theorems of these extremal black holes, how they square together. So that was.
Well, I mean, it's again, it reflects the point that there isn't an obvious, there isn't an obvious regular end state. So what that means is that somehow, that of course, we're used to thinking that, oh, instability of this sort of, we have, two critical points. Instability of this means that, okay, the solution will flow to the other one or something like that. But of course, in the world of PD, instability can just mean that things are growing and there's no stationary sort of endpoint. So, what you say is exactly correct, right? That, there is no other candidate endpoint. So, so in some sense, it would seem that the scenarios are either that you have stability, but in a coarse-grained sense, or, things just get worse and worse. So an example of things getting worse and worse that, you might imagine, and okay, it's more plausible this happens around extremal Kerr than around extremal Reisner-Nordstrom, but you might imagine that small-scale structure is forming near the horizon, and it just keeps on forming. So you could even imagine a catastrophe of, more and more little black holes forming near the horizon. Okay, and so as time goes to infinity, you just get, infinitely many little black holes at sort of smaller and smaller scales, etc., near the horizon. Do I think that actually happens? No. But okay, a priori, this is
extremal Reisner-Nordstrom, that may be feasible because you can sum up the solutions. You have multi-center black holes, but for Kerr, extremal Kerr, it's very far-fetched, you see. So,
well, certainly, I don't think that's, let's say, I don't think that's the the thing to bet on, but I think it is, on the other hand, useful to keep in mind that in some sense, that's the thing you want to show does not happen. If, because a priori, that's certainly the type of thing that can happen. If sort of perturbations are growing and you have no control anymore over the solution, then that is the type of thing that in principle could be happening. And so, I actually think secretly that there is some structure that makes things as good as possible given the instabilities we know occur. And so I would bet, to the extent that I'm a betting person, that it is as stable as it can be, consistent with what we know about linear theory. At the full nonlinear level, it is as stable as it can be, consistent with what we know. But that is wishful thinking, and the sort of the unwishful thinking would be the kind of scenario that I just said. And it would be very, very interesting to be able to understand, if the wishful thinking does pan out, why it pans out. And at present,
can I ask? Can I
actually,
change gear and ask one different question?
Sorry. I might. I know that we have gone significantly over time. I don't want to disturb this lively exchange. It's beautiful, but I also worry if our speaker has commitments or other constraints. So we can. How about this? Let us thank our speaker one more time, and then we're going to continue with maybe a few more questions. Mihalis, thank you very much for this beautiful and stimulating talk. And I'm ending the recording here.
Thank you for having me here.
Thank you again.
And I'm happy to answer any more questions.
Yes, please, let us continue.
Okay, thanks. So have you thought about the instability of FLRW type cosmologies, just to change the gear? So whether
instability towards the past or towards the singularity?
Towards the future. For example,